Welcome back to POE. Today we're going to be talking about moment. This is the second of our two-part series over moment. The first part we really went into great detail with the equation, and now we're going to start showing you where moment and how it's applicable. Well, the first step is where it comes into play is on, it could be like seesaw situations. This is really similar to our levers. It's exactly levers. But what we'll do is we're going to talk about it in terms of moment now. So in this, I want to say the sum of the moments are equal to 0. Let me see if we end up with a number with enough space here. We have our sum sign, which means that I can take the sum of the moments are equal to the moment of the little bear. I'm going to call this 1, and I'm going to call this one 2. I can say the moment of the little bear plus the moment of the big bear is equal to 0. Well, remember when we go back to our moments using the right-hand rule. Using the right-hand rule, that if I'm turning clockwise, right, that's going to be negative. So moment 2 over here, the moment that the big bear is doing is going to be negative. Well, that allows me then, if I take that to the other side, to say that moment 1 is equal to the moment of the second. Well, what is moment? It's force times distance. So the first force is 25 pounds times the distance, and it's 4 feet away. Remember, moment is in feet. The second one now is 40 pounds, and we don't know its distance. So 25 times 4 is 100, and that equals 40 times d. And then we can say that once I divide both sides by 40, we see that 2.5 feet is how far away the second bear is. And that all deals with moment because it's dealing with torques or turning here. Moment calculations. Alright, well in this situation here, I want you to imagine this being like a very simple bridge, or even just a simple platform. And what we're going to do is we're going to solve for RBY. So again, I'm going to start off by saying the sum of the moments is equal to 0. And I can say then that there is no moment here at A because it's fixed. They're saying put A as the pivot point. So C is creating a moment. It's making this bar want to turn clockwise. So I can say the sum of the moments is equal to the moment at C plus the moment at B. Moment at B. Now, one of these is going to be negative. If you go back to our last slide here, clockwise is negative right here, and counterclockwise is positive. Well, C makes it want to go clockwise, so that's going to be the negative one. Well, now I have one being negative and one being positive, so I can put them on opposite sides. The moment at C is equal to the moment at B. That might be a little bit confusing, but again, what is the moment of C? Well, that's force times distance. The force is 35 pounds times the distance of 3 feet. The moment over here, well, what is the force pushing up? What is this force? Well, we're now calling that RBY, the reactionary force on B in the Y direction. How far away is that? It's 10 feet away. Well, 35 times 3 is 105 equals 10 RBY. And we can say then that RBY is equal to 10.5 newtons. So RBY is 10.5 newtons. That tells me then that if this is 10.5 newtons, that this one over here, RAY, must be pushing up with 24.5 newtons. And why do we know that? Well, if that's pushing down with 35 newtons, then these two have to be pushing up with a combined mass of 35 pounds. I keep saying newtons, 35 pounds, because they have to be opposite and equal of each other. Otherwise, the bridge is going to fall if the bridge has a greater force pushing down. Okay, what I've done here is we've got, speaking of bridges, I guess, that's where I need to start off with, here's a bridge truss problem, which is really close to what we're heading into. The moment at B plus the moment at C plus the moment of D has to be equal to 0. That's the sum of the moments. Why? Because we've pinned it right here at A. It can't move at all here at A. So there's where we're saying our pin is. So by doing that then, we're going to be finding out the reactionary force over here at point D in the y direction. Again, it's at point D, that's why the D is there, and it's pushing up, so that's why we say it's in the y direction. Let's go back up here to these negatives. These are both negative because they're trying, if I get rid of this pin, if we get rid of this right here, what's going to happen? Well, it's going to turn, it's going to rotate, because it's going to be pinned here, so it's going to spin clockwise. Again, clockwise tells us that it would have to be negative. So I've got B would cause it to spin clockwise, and C would cause it to spin clockwise, so I've got them both being negative. I've got them moved to the other side now as I start to solve this equation. I've taken the negative ones, moved them to the other side, made them positive. So now it's just a matter of plugging in what we know. What is the moment at D? Well, that's force times distance. Well, over here, I don't know the force, so I'm going to put R dy times the distance. How far away is it from here? How far is its perpendicular distance away? Well, it's 32 feet away. On the other side, B, what's my moment at B? That's up here at the top. Its force is 500 pounds, so it's 500. All right, how far away is it? What's its perpendicular distance? That's right here, 12. Moment at C. All right, down here at C, the force is 600, and the distance is 24. Well, when we do all this math and add it up, that gives us the reactionary force at D in the y direction times 32 is equal to 20,400. And I believe this is in, this is pounds again. I keep wanting to say newtons. I'm used to my physics. Solve for the reactionary force at D in the y direction, and we get 637.5 pounds. So that means right here, this one right here, is pushing up at 637.5 pounds of force. Well, hey, I hope that was helpful for you today. We've done a lot of work yesterday with vectors. We did a lot of work here with the vectors, understanding which way things are going. And then we also really worked on moment. So hopefully that was beneficial, educational, and I'll catch you on the flip side.